Okay, this is for section 6.2. And this is on inverse functions. And relations. First, the author defines a relation. A relation is any set of ordered pairs. As long as you put it in the set notation, the braces. Like if I said I have the ordered pair 1, 2, the ordered pair 1, 5, and the ordered pair -4, 2. That would be considered a relation. It's any set of ordered pairs. Okay. If they ask you for the inverse of the relation, the inverse, you just interchange the x and y. If they give you a set of ordered pairs, so the inverse would be 2, 1, 5, 1, and 2, -4. Okay, and that is the inverse. Okay, if we do it graphically, okay, just a sketch of this, graph the relation first. So if I graph the ordered pair 1, 2, plot a point. The ordered pair 1, 5, put a point. And the ordered pair -4 and up 2, put a point. Okay, and I'm gonna connect those so you see a shape. Oops, I can do better. If I graph those, I get a triangle. Okay. Now do the inverse. So graph 2 to the right and up 1. Graph 5 to the right and up 1. And graph 2 and down 4. Alright, and you should get they are inverse functions, not functions, relations. Okay, and anytime you graph inverse relations, they are symmetric about the line y equals x. Okay, y equals x is going to go through, like y equals, if you did y equals x plus 0, it's going to go through the origin, go up to 1, up to 2, and if you just dash that line, inverses are symmetrical about the line y equals x. That means in terms of geometry, I could fold that graph over that line and that triangle would lie right on top of the other one. Okay, so they are symmetrical. So out at the side, put inverses are symmetric about the line y equals x. Okay, that's how visually you tell whether or not it's an inverse. Okay. Now algebraically, if they give you an equation or something and say find the inverse of this, the steps to find the inverse of a function. Now these are functions. Steps to find an inverse of a function. Number 1, you interchange the x and y. Interchange the x and y. Number 2, you solve for y. And then number 3, you write it as a function. So, as an example, say they asked you to find the inverse of f of x equals a negative 1/2 x plus 1. Y equals, or f of x equals a negative 1/2 x plus 1. First thing on this one, f of x is the same thing as y. So we can write it with a y in there. Okay, so actually there's a step up above number 1. Same, get it in the right form. Okay, now interchange the x and y. Okay, so make this an x, make this one a y. Now solve for y. Get y by itself. So I can subtract 1, multiply by, negative 2, multiply by negative 2 on both sides. Okay, and then that'd be a negative 2x plus 2 equals a positive y. Okay? And that is the inverse, but they will write it in the function notation. So you rewrite this y, instead of y, it would be f inverse of x. Don't read it f to the negative 1. You read it f inverse of x equals negative 2x plus 2. They are inverses of each other. Okay. Okay. So if we graph those two, okay, graph the original, or you can graph this one. Y equals a negative 1/2 x plus 1. So it's going to go through at positive 1. The slope is a negative 1/2, so down 1, and then to the right 2. Okay, you agree you're going to get a line that comes through something like that. And then graph this, and I'm going to graph it in this form. So now y equals, graph the 2, so it's going to go through at positive 2, and the slope is negative 2, so go down 2 and to the right 1, down 2 and to the right 1. My graph's a little bit off, something like that. And then if you graphed the line, we said this line, y equals x, it ought to be symmetric about that line. So if I went through this point should actually go right through. Okay, so let's stop there a minute. Okay, so you can see that those are symmetrical about that line, y equals x. Okay, and the other thing, if you look at the inverses, go back to the beginning inverse. The beginning inverse was take x times a negative 1/2 and add 1, and the other one is take x times a negative 2 and add 2. Okay. Okay, and we'll come back to that in a minute. Okay, the next thing the author goes through is two functions. Two functions, f and g, are inverse functions. IFF, if and only if both of their compositions are the identity function. And the identity function in this case is just x, like y equals x. Or identity functions. Okay? So, if they said f of g of x, or another way to write that, f of g of x, is going to bring you back to the identity function x. It brings you back to x. The difference on what we're doing is I'm not using, back in this original problem back here, I did not use f and g. I used f of x and I used f inverse of x. So for g, I'm going to use f inverse of x. So I can rewrite this as f of f inverse of x will bring you back to x. Go the other way. If you said g of f of x, that's one way to write it. Or g of f of x. If the composition brings you back to x on both those, then they are inverses. But I did not in that example use g. I used f inverse of f of x. Those two compositions should bring you back to x. That's how you prove that it is an inverse. What's up? Let me see. So they will ask you to prove that what we just did in example 1, that they really are inverses. And basically it's a way to, how do you check? How do you check it, that they really are inverses? So you do both of these. I'm going to do both of these as a check. Okay, if you go back and look at the one we just did in example 1, in example 1 our f of x was, what was f of x? Yep, negative 1/2 x plus 1. And the inverse that we got? Negative 2x, right? It was negative 2x plus 2. Now, we have to do both compositions and prove that we get back to x. Okay, so I'm going to do this one first. So let's do f of f inverse of x. Okay, so this says, do the innermost group first. Sub this in. Okay, so you're going to sub that in, put this in for f inverse. So you'd have f of negative 2x plus 2. Okay, and that just says everywhere you see an x in the f function, you're going to substitute this in. So you're going to substitute into this negative 1/2 and sub in a negative 2x plus 2, and we still have the plus 1. Multiply that out. What's a negative 1/2 times a negative 2? Just 1x, right? What's a negative 1/2 times positive 2? Negative 1 plus 1. Does it bring you back to x? Yeah. Okay, so that's the first part. Okay, I'm substituting this into the f function, so I'm putting that in right here. Everywhere you see an x. Okay, now I'm going to do this one. Okay, got a little separator there. So now I'm going to do f inverse of f of x. You have to do that composition and prove that it brings you back to x. So what's my f of x function? Yep, so I'm going to sub that in. For f of x, I need to put this in. So it's a negative 1/2 x plus 1. Okay? So that says everywhere in the inverse function, everywhere I see an x, I need to put this in. So sub that in right here. So negative 2 times a negative 1/2 x plus 1 plus 2. Okay? So you'd have, multiply that out, negative 2 times a negative 1/2. positive 1 x, negative 2 times a positive 1, negative 2, and then we still have the plus 2. Negative 2 plus 2. So does it bring you back to x? As long as they both bring you back to x, then yes, they really are inverses. Okay? So the functions, the two functions are inverses if they bring you back to that identity. They always have to bring you back to x. And you always have to check both of them. Okay? Okay, the last part. For the inverse of a function to also be a function, you can always find the inverse. But is that inverse also a function? For the inverse of a function to also be a function, the original function must be 1-to-1. Now, you can write it like that, 1-to-1, or you can write it like this. A lot of times I just shortcut it and write it 1-to-1. Okay? What's the test graphically to tell whether or not a graph is a function? Vertical line test, right? To tell whether or not it's a function. The test to tell whether or not it's 1-to-1 is the horizontal line test. If it intersects 2 points horizontally, it's not 1-to-1. Okay? Just like if on the vertical line test, if it intersects 2 points vertically, it's not a function. Okay, so this says for an inverse of a function to also be a function, the original function must be 1-to-1. So that means it has to satisfy both the vertical line test and the horizontal line test. Okay, so that means the original function must pass the vertical line test to be a function and the horizontal line test to be 1-to-1. So it's got to pass both. Okay. So if you went back up to our original example, okay, look at the original line. Go back up, look at the original line. The original line was the negative 1/2 x plus 1. That was this one. Look at this one. This one. Yep, that's this one. Okay. Does that line pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So is our inverse a function? Yes. Okay. No. There's more to it than that. There's more to it than that. Okay. It has to pass both those tests. Yeah. Okay. Okay. That's as much as I'm going to do.